I'll do a recap on what we were doing. We defined Coxeter polytopes, which are polytopes in either Sn, Rn, or Hn, which is the most interesting one for this conference, and in general, actually, with angles, with dihedral angles that are pi over some integer. Yeah, the microphone. Maybe the third time I will not forget the microphone. Okay, so we care about these Coxeter polytopes because we want to glue some copies of them together to build manifolds. So there's Selberg's lemma. That tells us that we can see the polytope as an orbifold, and there is a manifold which covers the polytope seen as an orbifold with a finite degree D cover. But we have not much control over D. This can be gigantic in general. We surely will have a lower bound because as we've seen before, we can compute some sort of Euler characteristic of P, which is a rational number. So this degree has to be at least the denominator to make it integer, since it's multiplicative over the cover. But yeah, in general, this could be a very big number and could be. So this is not a constructive lemma. We do not know how to find a manifold from this, and in general, is not an easy problem to. It is only easy when the angles are going to be right angles, and so in the second part we will focus on those. But first, I'll do some examples in this case, in the general case. So we were talking about regular polyhedra before. I drew a table that I drew again here about which regular polyhedra can be realized in the hyperbolic space and also in as Coxeter polytopes, also in the other geometries. So the idea is this. So every regular polyhedron has an Euclidean angle, which is just the angle that you measure when you are in the Euclidean space. When you want to build a copy in the hyperbolic space, you just take a copy of this polytope in the tangent space of one point, and then you take the vertices and you push them inside the hyperbolic space with the exponential map, and then you take the convex hull. And the angles are going to be smaller than the Euclidean ones in the hyperbolic case and bigger in the spherical case. And you can take, in the hyperbolic case, you can take a very small polytope. This is maybe a tetrahedron. You can take a very small, and the angles are going to be very close to the Euclidean ones, or you can go and push to the boundary, which is like sort of S2. I don't know how to. Let's do it like this. If you go till the boundary, you just measure one angle, that is the angle of the ideal regular polyhedron that you're considering, and this is the. After this, you cannot go. You cannot go after the points of infinity. So in the spherical case, it's going to be more or less the same. You take a very small one. It's going to be similar to the Euclidean angle. The limit is going to arrive at that. But if you take it bigger and bigger, as long as the injectivity radius allows you to then you get bigger and bigger angles. Okay, so this limit, so this table shows you that there's plenty of example of at least angles that divide 2 pi. So these two cases are not Coxeter. But I still decided to write them because they're useful for one of these examples. Okay, so so the first example I wanted to show you is a very famous example. I'm sure some of you have seen it. Let's say for now we just consider 2 tetrahedra and we don't care about the angles. We just care about topology for now, and we identify the facets of these 2 tetrahedra as prescribed as by what I've written here. So I labeled the 4 facets of the tetrahedra with some very non-symmetrical letters to encode the thing. So the red letters here are the 2 faces that you see above, like in front, and these are the one in the bottom and the one in the back. And I'm gluing this tetrahedra to this tetrahedron to this tetrahedron, gluing the facet as prescribed by how the letters are put here. So what happens to the edges? What happens is like this edge here is going to be identified also with this edge here in this way, because they're in the facet that I labeled with F, and also this one. This one is going together with this one, but this one is also below the Q, so it's also this one, and what else is here? At the left of the P, we have this edge, which is also this one. And the other edges, if I just follow through this edge here, let's do it like this, with another color and with a triangle. This one is also this one if you look at the facet with the Q. But if I look here at the F, it's also this one. But if I look at the P, it's going to be this one. And if I now look at the Q, should be this one here. So there's another one which is going to be, I guess, this one. Because if you look at the back face, the R, and you follow here, is going to be this one. So what happens is that edges group up 6 by 6, no? So when you look inside the manifold and you take one edge and you look around this edge, you're going to see the tetrahedra, like the 2 tetrahedra, you're going to see them 6 times. Because when you look at one edge inside the manifold, you see one tetrahedron for each of these 6 edges that go together. So that's these 6 in the manifold. And so we have an edge that's separating 6. No, around this edge you see something. This is a bit of a mess. Something like this. Now the space is separated into 6 parts, and each of these, if I just choose every angle around this edge of the tetrahedron to be pi over 3, is pi over 3, the total angle is just is simply 6 times pi over 3, which is 2 pi, which is like the angle that we should see around this S1 that goes around this edge. And so around the edges, the metric is preserved. And also, there is a tetrahedron in the hyperbolic space which has angle exactly pi over 3, and it is ideal. So these vertices are actually not here, and we don't have to care about the metrics around this. If this was an actual, the vertices will be like real hyperbolic vertices, we should have to also care that their link around the vertices is actually S2. But in our case, we're just considering an ideal tetrahedron, so we have a very explicit example of a hyperbolic trimanifold, which is just built by gluing, is triangulated by 2 tetrahedra. It has a cusp, at least. We can actually cut. We could cut and truncate the tetrahedron here and here, and just track how these triangles are glued together. We could, in principle, I mean, it's not hard to do, but I'm not going to do it because I'm going to get it wrong otherwise. And we can just track the triangles. They're going to glue in some way, which is, the spoiler is going to be something like this with a torus that's just, I don't know, something like this. And so we get a trimanifold which has 1 toric cusp as expected. And this picture actually shows, this is the complement of the figure 8 knot in S3. I think it's very hard to visualize. I will not try to convince you about this, but there's pictures online you can try and convince yourself if you have one day when you want to suffer, but looking at the picture for 24 hours and then realize finally when it's not easy. It's not easy to see, but you can compute basically everything about this manifold. You have a triangulation with also very small triangulation, so it's a very explicit construction. Okay, so also maybe a remark, which I don't have space to put. No, I'll make it later. I'll just hope to not forget. It's two tetrahedra that are glued together by this. It's encoded by this lateral approach. So this face F here is glued to this face F like this, and then this face P is glued to this face P at the bottom, and like just glue them to make the P coincide.
How many cusps does it have?
Just 1. It's just the complement of the figure 8 knot, because if you you can follow all these triangles here that are sections of the cusp. Like the section of a cusp is just given by these flat triangles that are here. When I truncate, I can just follow all the gluings, and if I just struggle for 5 minutes to follow all the gluings, I get a picture like this, and it's only one. They're all connected. You can, for example, like this line here is connected to this line here, and then maybe you go here, which is on the face Q, which is going to be whatever, this one of those, maybe this one, and then you go around and you touch all of them when you don't have to. But yeah, in principle you can get many, and okay, the remark I wanted to make is like, now you get a torus, and it's just obvious that you're going to get a torus because it's orientable, and it's the only closed flat surface that could happen. But if you just, for example, take 4 manifolds, you could have like non-toric cusps, and you can see by the picture what the cusp is. It's very explicit. This is what I was trying to say. So the other example I wanted to make is with the dodecahedron. So this is actually 3 examples in one. So I just take only one copy of the dodecahedron, and I glue it together with itself by choosing a pairing of its facets. So every facet is going to be paired up with another one of the dodecahedron. And I pair every facet with the one at the opposite side. So there's 12 of them, and they're paired up. This one is opposite to this one here is opposite to this one here in the back, et cetera, et cetera. And they're off by 1/10 of a rotation. Now these facets are not actually identified by translation. No, they're opposite. So you can decide how to glue them by, say, identify opposite facets. I just need to, I can do it in many times, no? In many ways. One way, for example, I can just rotate, let's say, this red edge here can be identified with, maybe I can just rotate just a tiny bit, and then they identify it with the yellow edge, which is a 1/10 rotation. Or I could maybe identify it with this edge, which is maybe green of green is not a good idea, but this is a 3/10 rotation. Or I can just go on the opposite side and identify it with this one, which is 5. It's like just a half turn. So there's 3 possible identification. They're like, if I go here, it's just exactly as doing the green one. It just mirrored on the other side. And so if you just compute this, all 3 of them are going to be manifolds. The links of all the vertices are going to be S2. But what can we say about the manifold that we get, for example, from a geometric point of view? I'd try to leave the details as an exercise tomorrow to see this, but so what's happening if you do a 1/10 rotation, then you are going to group the edges in groups of 3. Here, they're going to be grouped in groups of 5, and here just in groups of 2. So in this case, one edge wants to see the dodecahedron with an angle of 2 pi over 3, so that when you glue 3 of them, the sum is 2 pi. Here you want to see an angle of 2 pi over 5, and here you want to see an angle of pi, which is a bit weird, but is actually realizable in the spherical geometry. So if you look at this table, and just trust me when I say that this is realizable in S3, this also with the dodecahedron is realizable in S3, and 2 pi over 5 is realizable as a hyperbolic polytope. So in fact, here you get a hyperbolic manifold, which is called the Seifert-Weber hyperbolic dodecahedral space. And here you get a spherical manifold, like an elliptic manifold. Here maybe exercise is a bit a clown of an exercise. It just what manifold is this, the red one? Is once you come up with manifold could it be, you say, yeah, okay, it must be like that. But these two examples are actually interesting. Okay, so what about?
There's fourth example on your table.
You mean here? Yeah. Okay, yeah. If you, maybe you cannot do it with one. Maybe you can take more dodecahedra and glue them in a weird pattern, and then having the edges going 6 by 6 instead of group of 5s, and then with that you can endow the manifold that you've built with a metric, which is going to be hyperbolic, and all the vertices represent cusps. But you, of course, I don't know, like there could be either one or more cusps. You just have to follow what happens when you do all the gluings. And yeah, for example, I will show you a general method in the end to build hyperbolic manifolds using right-angle polytopes. There's a more I don't know how to say it. A more, let's say, a way that just works. You just codify something, and then you build a manifold automatically without having to guess some gluings. And that will be an example. You can build many examples using this. Okay, I'll try to tell you about an example in dimension 4. Of course, I'm not going to draw it, but so I told you in dimension 4 there were 6 regular polytopes. I'll tell you about my favorite ones, which are the 120 cell and the 24 cell. The 120 cell is an analogous of the dodecahedron, so it has 120 facets which are dodecahedra. It actually has 600 vertices. It has 720 edges and 1,200 two-dimensional faces, which are pentagons. So much bigger than the examples you see here, but it's still manageable. So this this can, so the Euclidean angle is about 70.32, and if you look at the ideal angle in H4, oh, that's the opposite. The ideal angle in H4 is 144, so you can realize it in, if you take an angle, you choose your favorite angle in this interval, you can realize it in H4 with this. And this is very nice because it contains 72, which is 2 pi over 5, and also contains 90, which is our favorite favorite angle in absolute. And the other very nice example that is very often used in dimension 4 is the 24 cell, which has 24 as the name facets, which are octahedra. It is self-dual, so it has 24 vertices, and then has 96 edges and 96 triangles as facets. So it's quite more manageable, and this is realizable. So let's say like this, like if you take the ideal regular 24 cell, this has the dihedral angle pi over 2, which is somewhat an analogous of the fact that the octahedron, the ideal octahedron in H3 has angle pi over 2. So these two have been like very useful tools to build some explicit examples of hyperbolic form manifolds. So the first, I think this is maybe the first example of a closed, like explicit closed for hyperbolic form manifold, which is Davis manifold, which is done like this. It's very similar to the example with the dodecahedron over there. So you take one copy of the 120 cell. And as I told you before, here, the two pentagons that you see at the opposite facets, they're not identifiable with a translation, they're sort of opposite. But in the 120 cell, this does not happen. And opposite facets are actually identifiable via translation. So you just do that, you just glue it, and you just maybe get lost in the combinatorics of this, but it's like not insanely, it's not insanely big. You can still see that if you take the ridges, which in this case are two-dimensional, no? In codimension 2, in dimension 4 is 2. You see that the pentagons are glued in groups of 5. So you can take 120 cell in H4 with angle 2 pi over 5, and you just know that you have a manifold that's tessellated in copies of this 120 cell exactly, and this model locally looks like the tessellation of the 120 cell of the whole hyperbolic space. And this is still, as before, very explicit, and you can compute everything about this manifold. You can compute the homology, you can compute the intersection form. It's very explicit. For example, maybe quite painful exercise. If I call this manifold M, its Euler characteristic is 26. And the Euler characteristic in even dimension is very important because, as you probably know, the volume of the hyperbolic manifolds in even dimension is proportional to the Euler characteristic. It's just quantified, no? So if I take like the volume of a hyperbolic 4 manifold, this is just going to be 4/3, I guess, pi squared times the Euler characteristic of the manifold. So one can try and say, okay, I want to build the manifold of minimal volume and try to glue small polytopes in a way to build a very small manifold. In this case, we have a bound of 26. Then I think there's an example of chance which goes down, builds something with Euler characteristic 17 with and the manifold is built with two right-angled, let's say, pi over 2 dodecahedra, 120 cell. And then, for example, now the things that we know about the volume is that the Euler characteristic must be even for a closed 4 manifold, and we have an example with 8. But in principle, there could be smaller examples. What? Sorry?
Can you repeat the sentence you just said?
So a closed orientable hyperbolic 4 manifold has even Euler characteristic. Yeah, either that or I forgot the. I think it's not orientable, yeah. Yeah. Thank you. Good spot. You're always very aware. Okay. So let's delete this. But if you don't care about closed, then this ideal regular 24 cell, also with angle pi over 2, also as Euler characteristic with the weighted alternating sum that I told you before, is just 1. So if you manage to build a 4 manifold using this one copy of this 24 cell, you get something that's not closed, but you get something that's minimal volume. And in fact, Radcliffe and Chance did exactly that. They sort of list every possible phase pairing of the 24 cell, check which give rise to a manifold, which are orientable, which, like, you just check whether the edges groups 4 by 4, so you have 4 angles of pi over 2 around. So this is just classify, maybe list would be better, all phase pairings. And they just write a computer program and they get, I guess, if I remember correctly, this number of manifolds. So this number of hyperbolic manifold which have minimal volume, and only 22 of these are orientable. So of course, sometimes the computation gets hard, no, and you just use a computer. It's very computer friendly because you're working with basically tessellations and triangulation. There's a reasonable way to codify. Okay. I'll go. So this is sort of on the good news side. You can use Coxeter polytopes and also polytopes that are not Coxeter to build interesting examples. And now the caveat, the bad news, is that Coxeter polytopes are frequent in low dimension and then sort of fade away. So when the dimension is 2, you just, with the technique I told you before, you just have, you take an, I just called n this, you take an m-gon. The Euclidean copy of this would have sum of angles m minus 2 over pi, and if the sum of angles is less than this, you can realize it in hyperbolic space. In the hyperbolic plane. So you just get a lot of them. Basically, almost every possible Coxeter polygon can be realized. In dimension n equal 3, then there's a beautiful theorem of Andreev, which basically tells you that so exists a polytope, let's say polyhedron, with combinatorial structure, with a fixed combinatorial structure, and angles. If and only if some conditions are met, some explicit conditions are met, and these are very last conditions. Like, it's basically, if there is no obvious obstruction, then the polytope exists. So there's many Coxeter polytopes in dimension 3. You can build basically everything that you want as long as you're reasonable. And then they start fading away. So in dimension 4, there's some examples. There's a lot of examples that are nice, and also, like, there's many. But then they sort of stop existing. So if you take, let's say, if you want a compact polytope, then we know examples only up to dimension 8. And not only that, but it's also proved that if the dimension is at least 25, then no polytopes. So, okay. Compact. Yeah. Compact. It's 30. Okay. Let's say 30. And if you want them, maybe you don't care about compact, maybe finite volume is enough for you. This is, of course, in HN. Otherwise, we always have some examples. So, okay, maybe you want finite volume, but also we know examples up to dimension 19, and we know one example in dimension 21. And also is proved that if the dimension is more at least 996, then no hope. So okay, so I guess what this teaches us is that, okay, they're very useful to give you explicit stuff, but then you cannot hope to just have something that works in general forever for every dimension with these techniques. Okay, so I'll probably make a short pause in a second, but before next part, we're going to talk mainly about right-angled polytopes. Okay, the question.
So can you, I mean, it's probably a hard question to answer with like a sentence or two, but like, can you say why? Or are there any intuitions for why they stopped existing? The compact case after 30?
So I don't know the exact proof, but there are some inequalities on the number of facets and stuff like this. It's some combinatorial conditions. There's some combinatorial inequalities on the things, and they just at some point they're not possible anymore to be satisfied. I think I can direct you on the precise paper that proves this stuff, but I don't know on the top of my head exactly. Maybe Misha knows. Okay, yeah, I'll briefly tell you about what happens when you take right-angled polytopes in this table. If we add, oh, this is a bad color. Red was better, right? If I want right angles, then with compact case, we know only example up to dimension 4, and it's actually proved that we cannot have it in dimension 5 or more. So these, which are the most useful, actually stop very early. Dimension 5, 6 are still low for some standards. And here we know examples only up to dimension 8. I think it's proved that after dimension 12, there cannot be. Sometimes I've seen 14. I think 12 is a new estimate. I don't know. Maybe I'll write 14 also. I think it's 12. Okay, so we'll take a pause, and then I'll try to explain some techniques explicitly with right angles polytopes. Okay. Apparently, I remember to turn on the microphone, so this is progress. So now I'm going to restrict to right angle polytopes. Which just means that I don't only want all the angles to be divisors of integer divisor of pi, but just all angles are pi over 2. And I restrict to this case because there's a much more general construction to build a manifold that when you have a Coxeter polytopes, you know you have a manifold, but you cannot build it explicitly. You have some work to do. And here there is a general construction that produces you a manifold that tessellated in this polytope. And the construction is the following. It starts with a coloring. So what is a coloring for me? I'll start by stating it a bit more particular, and then I'll say something a bit more general. So we start with a polytope P and a coloring for P, let's say a C coloring, is the association of a color in a palette of C colors to each one of its facets. Following a rule such that two adjacent facets do not have the same color. So, for example, if you have a right angle hexagon, you can just color it with two colors. Is this just alternatively? No? And for example, one other meaningful example could be this one. There's the ideal this ideal octahedron. I told you that in H3 it can be realized with right angles. We can color it by taking a checkerboard pattern. Is there a more reasonable yellow? Maybe not. I can color in red and yellow alternative in sort of a checkerboard pattern, and you might think that these two red, this is also, should write the top before the thing that's behind. You can think that these two red facets are touching, but they're touching in an ideal vertex, so they're not actually touching, so the condition is satisfied. So this seems like a very basic notion. Why does it build a manifold? So there's basically three ways to see this. First, I'm gonna give not many details on this one, but there is an algebraic way to see it. It's just you can consider the group of reflections along the facet of the polytope. And I told you we want to find a torsion-free subgroup of this one. And this coloring allows us to build a map from this group to Z to Z to the C, which is basically taking one generator, which is a reflection, and sending it to the element of the canonical basis associated to the color of the facet F. And then you can take the kernel, and you can verify that the kernel is torsion-free. You can verify explicitly that every maximal finite subgroup is going to map injectively. This is basically the way that the coloring is defined forces you to have something. But like, I don't want to prove it explicitly because there's a couple of ways that are way more geometric to visualize this, because as before, we don't want just to know that a manifold exists, but we want to have an explicit description of the manifold so that we can actually compute stuff on it. So there's a construction via doubling along all colors. So how do you build a manifold from this hexagon? You double along all colors. What does it mean? It means you take this hexagon, you choose one color, you take 2 copies of the hexagon, and you glue them along the edges of this color. So this means, for example, if I took this hexagon here, this right angle hexagon, the colors are visible, right? No, I'll try and choose some, maybe I'll just use white instead of yellow, since it's more bold, you can see it. Okay, so what happens if I double along white? Means I take 2 hexagons and I glue them together along the white edges, which is just doing this. I end up with a pair of pants. And what happens, the right angle guarantee me that when I'm gluing this part on the left and this part on the right angles guarantee me that this is just totally geodesic. The boundaries keep being totally geodesic. And then this picture is basically also this picture. I just rearrange everything like that. And then what happens if I double along red? It means I take 2 pictures of this and I glue them along the red edges, and so I get just a genus 2 surface which has some white and red edges drawn over it that divide it into 4 hexagons. So this is actually the number of polytopes that I have doubles every time I do the doubling, and so I get a manifold M tessellated in 2 to the power of number of colors copies of the polytope. So it's actually a very simple construction, very easy to understand. And you actually just need a coloring. And the coloring always exists because you can, of course, choose as many colors as the number of facets, and then you just double that many times and you get. Of course, most of the times you don't want to do it if you want to actually work with your example, because if your polytope has 120 facets and you choose different colorings, you get 2 to the power of 120, and then you cannot work with that example actually. So finding efficient coloring is actually sometimes a limiting factor. So another third way to see the same exact thing is to just take 4 copies of the hexagons and codify all the gluings at the same time. So you can take 4 copies. I'll change red to orange. Is it better or is it worse? It's worse? Okay. I'll keep red. Yeah. Oh, but I get confused in the end if I do that. So I get so I have 4 of them at the same time, and this I have this vector space z1 to z to the c, and I can give a name to each polytope. I have 2 to the power of c polytopes in the end. I can just give them a name with a vector of this. So I will call this 0, 0, this 1, 0, this 0, 1, and this 1, 1. I can just, and then I can also choose that the white is the first color. I call the element of the canonical base E1, and red is the second one. So E2 or vertical direction if you want. So how are the gluings codified? It's just that if I have to glue every facet, no? I have to choose a facet. So take a facet, take a polytope PV, where V is a vector, and I take a facet. To what will I glue it? Glue with identity to the same facet of the polytope P, V plus E I, where I is the color of the facet. So very easy to remember. So here I told you white is horizontal and red is vertical. This means that this side is glued to this side with the identity, because we move horizontally when white. This side is going to be glued to this side. This side is going to be glued with this side. And analogously, this one is going to be glued to this one and same with the other. With the red one, it's going to be the opposite. So this side here moves vertically, is glued to this one. But we always choose the same and always with identity. And so, for example, this one is to this one is to this one. And so this can also give us an idea to generalize this construction. if I want to keep the analogy with the colors instead of the vector space, I can say I paint every facet with some colors and not just one. But what can I do instead? Instead of associating a color, let's say a generalized coloring, is to assign to a facet, we assign a vector v in z mod to z to the c. And then we ask some conditions that are going to be a bit more complicated than those one, which are going to be that if, let's call it, so if facets touch in a real vertex, then they have to have their vectors are linearly independent. And some other condition with the if facet touch on some ideal edge, then the same. So this is basically the same construction made a bit more complicated so that you can build more interesting examples. But these examples are often interesting enough, so I will, for the purpose of like the whole mini course, I will just refer to this. There maybe will be some exercises that involve having this more complicated version of the coloring construction. So, okay. So for my third lecture, the objective will be to build a map from hyperbolic manifolds to S1 and study them. And we will use right angles polytopes. So I will now try and build some structure to do manifold, to build these maps. So the goal is to arrive to prove this theorem myself with Bruno Martelli and Matteo Migliorini, such that there is a cusped hyperbolic 5-manifold, which is a fiber bundle over a surface, over a circle, which fibers over S1. So what we want to do, the goal is to find a way to use the coloring construction and build maps from M to S1 and then study them. As an example of something that you can do quite not too painfully. So yeah, let's delete this. Okay, so this tessellation of the manifold into right angle polytope is very nice, but there is something that's even nicer, which is the dual of this tessellation. So every time you have a tessellation, you can look at the dual. What is? For every polytope that you have in the tessellation, you choose a vertex. Every time two polytopes are connected by their facets, you connect them with an edge. And everything that's d-dimensional corresponds to something that's n minus d-dimensional in the dual. So for example, here, let's torture this part of Blackboard. I don't know if I can, let's try purple. It's gonna be. So this is a tessellation of a surface of genus 2 into 4 hexagons. I'm gonna take the dual. So I have to take one vertex for every hexagon. Then, for example, there's these 2 hexagons here are glued along this white facet, so there's one edge that connects here. But there actually are 3 edges that connect all this. Now this, I don't know how to maintain that. These are 3 different edges. But there's also one edge that goes through this and arrives here, and the same way. And then there's this vertex here, which is actually glued via the red one to this one, which is glued to via the white one with this one, and with the red one with this one. So it's the same vertex in a tessellation, will correspond to a square. So there is a square. So this here is going to be one of the squares in the tessellation. And there's actually going to be 6 of them. They're just the 6 vertices. So we started with hexagon and we ended up with squares. And this is not just something that happened by chance, because when you build something that's right angle and then you do the dual, you end up always with cubes. So this is the this is the bad chalk. Dual to tessellation with right angles. The dual is a cube complex. So all 2-dimensional cells are going to be square, all 3-dimensional cells are going to be cubes, 4-dimensional hypercubes, and then we get something that's way less chaotic and way more symmetric of this. And in fact, the vertices correspond to the polytopes, and so correspond exactly to the vectors here, and here this is exactly the one of the cubes that you see. No, okay, I'll have to choose what to do in these 12 minutes. Okay, so the idea for the day after tomorrow is to take this cube complex C and build a map from C to S1. And then to build this map, then we will want to study it, and in doing so, we will often pass from the tessellation to the dual and have a way to represent everything in both situations, so that we can visualize the things where they're more convenient to visualize. So, in short, what is a way to build a map from a cube complex to S1? So S1 can be seen as this cube complex. There's one vertex and one edge. And for example, to define a map, I have a cube complex, which is some cubes glued together, I don't know, and so the first thing I could try and do is at least I'll define it on the one skeleton. So and I want the vertices to go in the vertex, and the edge, I will just choose whether the edge is going to be mapped looping like this or looping like this. And a simple way to encode this is to just draw an arrow on the edge. So how to map it to S1. So I'm starting from this point. I can just draw some arrows. That's maybe I'll draw. No, I'll make another picture here.
So you want all your edges to map subjectively to this one and bijectively outside this one. So you don't want your edges to go to a point.
Yeah, the edges will never go to a point. I will just, yes. So this construction, so in some sense, the map that I want to build will try to go diagonal on every cube. So it will. So I want to build this map to study it as a Morse function. So I want just the points to be critical. So the maps will go every edge and only the edges are going to be mapped stationary here. Only the vertices are going to map on the cube. So, okay, so the orientation on the cube complex is just a choice of arrows, and I don't have space, but if I add here the word coherent orientation, a coherent orientation is going to be something that's a choice of arrows such that on every square it goes like this. Every time I see a two-dimensional square, the two edges that are opposite have the arrow in the same direction. And I want to convince you in this last minutes that a coherent orientation already gives you a map to S1 on the whole cube complex. This map can just be extended to everything. So it gives a map on the one skeleton. That extend to the whole cube complex. And how does this work? So the point is that when you have a coherent orientation, and you have, this is horrible. Okay, when you have a coherent orientation, and let's draw it like this, and you take one cube, of any dimension. Here I draw a three-dimensional one because I'm not going to try to draw an hypercube now. What happens when you build, when you have a coherent orientation, there's always a vertex of the cube. Well, all the arrows go out, and on the opposite vertex of the cube, all the arrows go in. So now this cube is actually identifiable with the standard cube inside R3. We just put here in the origin the vertex where all the arrows go out, and then these three arrows determine everything because of the coherence. And now we want to build a map to S1. And here, so we have a map from 0, 1 to the n. We have 0, 1 to the n. We want to build a map to S1. I built first a map to R, and then a quotient into R mod Z, which is S1. How do I do it? I just go diagonally. So the arrows here in this point are just pointing outwards, and from this point I just go diagonally on the diagonal of this cube. So more precisely, what I do, I take the point x1, xn here, and I map it to x1 plus x2 plus xn, and then project to S1. So this coherent orientation, of course, is a condition that's very strong, and in particular in the theorem it cannot be guaranteed. It can be almost guaranteed, so there's more work to do. But so the issue to build map to S1 is to just try to define it on the two skeleton and try to extend it. It's like there's way to extend maps that are different than this one. We'll probably talk about them in 2 days. But so I guess the takeaway is to try, so use this cube complex structure to so this particular manifold built with right angles have also this symmetric dual that's very useful to do construction on. And okay, so there's a question on this, otherwise I'm finished. Okay, so I'll finish.